the problem that I asked you to work out for next Tuesday, having to do with calculating flow rates of various streams from a continuous still. It's an example of how you write a balance with respect to all or some of the components in order to calculate the desired information. So I'm not going to work this problem for you, but I just thought it might give you a couple of hints here on how you'd proceed. And this problem has to do with calculating the feed and calculating the product rates for a particular instance where the feed mixture to a continuous fractionating column is 10 weight percent, 10,000 pounds per hour, and some other things are given here. And the first step, as I've suggested in a working problem of this nature, is to draw a little sketch, simple flow diagram of the process so that you can visualize what it is. And in this case, all you need to do is to draw something representing a distilling column. Draw an arrow into the mid portion somewhere which indicates the feed, and recommend you put on alongside what the explicit data that's given. For example, this was 10,000 pounds per hour and was given as 10% by weight. There's also a statement that the steam is introduced here in live steam for heating, and that there's a heads product which we'll call H, and there's a side stream product which we can call P, and then there's a bottoms product. The concentration of alcohol in these three streams were given, so you can put that on there. But you don't know what the rates are. I don't bother to write them on here, but the X of P is known, and X of B is stated, and the the composition of the heads was given. So that would be the first step. Then, in order to solve the problem, you make use of a material balance, a mass balance. In the first case, the overall mass balance would be simply written using our symbols, that what enters the system is the feed plus the steam, and this has to be equal to the mass of the outgoing stream, which is H plus P plus B. Then there's certain relationships stated in the problem between these streams, and so that'll give you a certain amount of information, a certain amount of relationship that can be used to solve the problem. The second step is to, in other words, we'd call this an overall mass balance. And then secondly, the next step frequently is, and in this case it is, to write a mass balance with respect to one component. In this case, we'll write a mass balance with respect to alcohol, or an alcohol balance. And what do we do there? We simply multiply the rates of each stream by its fraction of alcohol in the mixture. So in other words, writing the relationship in terms of our symbols, we'd have F times X sub F plus S times X sub S is equal to H times X sub H plus P times X sub P plus B times X sub B. Some of these are given. Those are not subscripts, or And so most of those, so you can put those in, and then you have another relationship. And as it works out, there's enough information, you end up with being able to substitute this into that, or vice versa, and solve for the unknowns. It should be obvious, of course, that that this S stands for steam rate, and we don't normally anticipate any significant amount of alcohol in the steam supply. So what would that be? It makes it 0, of course. So that's a procedure you start with. Are there any questions about that? So then now I would turn to continue the type of discussion we had last period, in which we discussed the concepts of vapor pressure, the pure components, and partial vapor pressure, or the components of mixtures. We mentioned that we're interested in quantitative relationships, and the simplest one applying to solutions or liquids is the concept of an ideal solution, which is mathematically represented by Raoult's law, or the statement that the partial pressure of a component of a mixture is equal to its concentration times the pressure it'd have in the pure state. This is Raoult's law, applying to an ideal mixture, and it applies to the liquid phase. Now we have another concept that pertains to the gas phase, the vapor phase, and as far as the laws are concerned, it's frequently referred to as Dalton's law, and this applies to the liquid. Now we're talking about the gaseous phase or vapor phase. Dalton's law, which can be written in mathematical form or equation form, would be something like this. The total pressure of a system is equal to the sum of the partial pressures. P sub A plus P sub B plus P sub C plus however many components there are in the mixture. The total pressure is the sum of the partial pressures of the separate components of the mixture. And furthermore, the partial pressure is a measure, as we indicated before, of the number of molecules of a given species or component acting as if it occupied a given space alone. So the partial pressure of a component of an ideal gas is a measure of its concentration in the mixture. And this leads to an expression which says that P sub A, the partial pressure in the gaseous phase, is equal to the concentration in the vapor phase times the total pressure of the mixture. In other words, the partial pressure due to some component of a gas or vapor is directly proportional to that fraction of that component in the mixture times the total pressure of the system. This is said to apply to ideal gases and or perfect gases, and this expression can be readily derived from the perfect gas law, which you have had in chemistry, which says that the pressure times the volume is equal to the number of moles times the gas constant at a particular temperature. And if we wanted to write it out then for component A, the partial pressure of component A would be equal to the number of molecules of A in a given volume times RT over V, this particular volume. And similarly, we could write it for component B would be partial pressure would be equal to the number of moles or molecules of component B times the same constant and the same volume. And of course, P sub C, if we had a ternary mixture, N sub C times RT over V. Now, if we add these together, we have that P sub A plus P sub B plus P sub C plus any other fourth one if we have it, which is equal to the total pressure, is equal to N sub A plus N sub B plus N sub C plus however many terms times the common factor RT over V. Now if we divide, let's say this is equation 1 by equation 4 here, dividing 1 by 4, we'd have the P sub A over the total pressure is equal to the number of molecules, number of moles of A in a given volume, divided by the sum of the moles, N sub A plus N sub B plus N sub C plus however many there are. And of course, what is this? The number of moles of component A divided by the total number of moles is what? It's the mole fraction in the vapor phase. And we use the symbol Y sub A to indicate the mole fraction of component A. In the gaseous phase, or the vapor phase. So in other words, this is the same expression we have here. P sub A is, so P sub A is equal to Y sub A times the total pressure. We can combine this expression and Raoult's law and get an expression so that we could actually calculate or predict concentration for a particular component in the vapor phase. It would be in equilibrium with a certain liquid composition if we can assume that both the vapor and the liquid were an ideal mixture. In other words, we're interested in knowledge of the composition of a vapor that's in equilibrium with a mixture, and there are two ways to obtain it. The most direct way would be determined experimentally, and of course this has been done in the case of our system that we're primarily interested in, alcohol and water. It's been measured many times by many investigators. In fact, it's been measured so many times that it's used as a standard to check on equipment to see if they perform correctly. Most anybody that designs a new piece of equipment, usually called an equilibrium still, to determine vapor-liquid equilibrium of a given system, will frequently check it against alcohol and water because it's been so much established that very little question about it. No, very little question about any errors involved. But of course there's Many compounds that are well known, but there's literally thousands of organic compounds that might be involved in a distillation process, or might be where there might be some occasion to produce or separate a mixture of organic compounds. And if you'd stop to calculate, if you took, I don't have those figures here, but if you had 5,000 maybe potential organic compounds that you're interested in, likely many of those have been studied as binary or sometimes ternary mixtures. But if you stop to calculate the number of combinations of binary mixtures, it might run into the 500,000 maybe, or something like that. I can figure it out, but I don't have the figures. And so the likelihood of all the possible combinations having been studied is very remote, because it's very laborious to determine. It's rather laborious to study a system thoroughly and get the data. So there's still a great interest in being able to estimate vapor-liquid concentrations from properties of the individual components. Now we'll not go into that very much, except that perhaps next time I'll have a little problem which shows a technique that you could use in the simplest case of combining expression for Raoult's law and Dalton's law to calculate the anticipated equilibrium information, assuming it was an ideal mixture. I'll have a little problem probably to illustrate that, in which we compare, which we'll calculate the values we'd predict for ethanol water and then compare it with experimental values. I forgot what else the point I was going to make about that. Oh. Well, I just might mention also that that we saw last time that frequently the partial vapor pressure, as predicted by Raoult's law, of a mixture is typically somewhat greater than would be predicted for an ideal mixture, which therefore caused the vapor pressure curve as a function of composition to be somewhat greater than a straight line connecting the two partial pressures, the two vapor pressures. Better draw that again. If we plot the partial pressures of the individual components against concentration in a mixture, and we have this value that would indicate the partial pressure of pure component A, and then this would be the this would be the pure pressure, this would be the partial pressure in a mixture. And similarly from for some other component B, this would be the partial pressure B for the ideal situation. But in reality, they're somewhat greater than the straight line would indicate. So the total pressure, instead of being a straight line across here, is something that's a concave with respect to the axis. This would be the total pressure, which means, of course, that this term is somewhat greater than would be predicted, and this can be handled, or the technique by which this is handled, and I'll just mention it with that, because you may find that in your reading that you'll find that Raoult's law is modified by introduction of another factor, which is called the activity coefficient, where the so that the expression would be the partial pressure of A would be the activity coefficient times the concentration of A times its partial pressure in the pure state, where gamma is equal to the activity coefficient. And gamma is usually greater than 1. However, it's not a constant. It's a function of the concentration. So there's various fairly complicated techniques and expressions for calculating vapor-liquid equilibrium by some device at getting at values of the activity coefficients, which we won't go into. Maybe later I'll mention certain equations that are used, such as the Margulies equation and Saturated equation that are based on these, and the properties of the pure components. I didn't mention a moment ago when we were talking about that generally the chemical properties, including the vapor pressure as a function of temperature for pure components, is usually readily available in the literature and handbooks or reference sources. But anyway, to get back to something a little bit more realistic for us, we saw last time how if this represents a fairly typical case, that that reversing this to measure temperature of the boiling point at a given total pressure results in a boiling point curve, which is has a reverse curvature, so that if we plot x of A again against temperature for, say, a binary mixture, where this is percentage of A, and of course the percentage of B would be the reverse of that, that we'll get a curve that has this general shape, and we can call that the boiling point curve. Represents the temperatures at which various mixtures would boil. This value here, of course, as I've drawn it, would be the temperature of the boiling point for component A, and over here would be the boiling point temperature for component B. So this is very useful, just having this much information, because it tells you that what the temperature should be, if you know what the composition of the mixture is, or conversely, it's more useful, if you know what the temperature is at the boiling point, it fixes the composition. As a matter of fact, we make use of that in determining one method of determining the percent alcohol in wine, the bulioscope or buliometer. You simply determine the boiling point of the mixture and read it from a table or a chart, and it gives you the percent alcohol in water. And that's what we can do, and that chart I had that last time is for that purpose. Now, as I said, we're interested in this information, but we're particularly interested in the composition of the vapor that's evolved from a particular mixture. And we can either do that by making calculations from our methods as indicated, or do it experimentally. So anyway, for a typical or normal solution, we would find that by taking various mixtures, determine the boiling point, the vapor evolved will be given by that which is indicated by a straight line across to this curve here, which we call the vapor curve, vapor composition. And so now we have a chart here which represents what we call the boiling point composition diagram, or phase diagram. As I indicated before, and if you're representing a temperature composition by some point below this curve, we have it would be a liquid phase, all liquid phase, and a single phase. Any point in this region here represents a mixture of liquid and vapor. Right? If we was right here, this would represent all liquid at the boiling point. If we're over here, this would represent all vapor at its boiling point. And so in this would be two phases, liquid and and vapor. And any point above the curve would be all vapor, one phase, and this would be, of course, a superheated vapor if it's up above the curve. So we call this a boiling point composition diagram. Or a phase diagram. Now, whereas that's very useful for many purposes, we don't particularly need to have the temperature represented on the chart, so we can simply take particular values here of the liquid composition and determine or read off the composition of the vapor, and so we plot that against each other, which gives us a chart where we plot the liquid composition on the horizontal scale and the vapor composition on the vertical scale. Since we're talking about vapor now, we'll use the symbol Y. And of course, these would be usually on the same scale. And so we typically draw in an X is equal to Y line here as a reference, but if we took a system that looks like this and plotted the points at which the vapor and liquid are in equilibrium, we would find that we'd get a curve that would have some shape like so. And so we call that the equilibrium curve, or the XY curve. XY diagram. And so it's a very useful chart or graph to solve certain types of problems, because it tells us the numerical values of compositions of the vapor that's in equilibrium with the liquid. Well, okay, now while I'm on that, I'll indicate that the one I've drawn here would be typical of what we call a normal system, or a normal binary system. Mixtures that two liquids that have no particular interaction with each other, such as methyl alcohol and ethyl alcohol, methyl alcohol and water, benzene and toluene, many others. Generally, compounds that are not too far apart in molecular structure will behave as normal mixtures, mutually soluble mixtures. And so we call that a sort of a normal solution. Remember that this does not represent an ideal mixture necessarily, although some systems where the two components are very close together, behave almost as an ideal liquid in the liquid phase. And also, I forgot to mention a while ago that, generally speaking, gases or mixtures of gases at low pressures, such as atmospheric or less, with very few exceptions, can be considered to be ideal mixtures. They behave as ideal gases. The reason for that is particularly the fact that the molecules are far enough apart in the vapor phase that there's no great tendency for interaction with each other, interference with each other, so the concept of Dalton's law is applicable. Well, anyway, this represents what we call a normal case. Now, ethyl alcohol is an example of one which behaves slightly differently. And we have a class of binary systems that are still, we're talking about mutually soluble systems, where if we plot the composition of the liquid against the vapor phase, and I'll just briefly quickly sketch in a little diagonal here for reference where x is equal to y, we'll find that we may have a system that comes back to the diagonal here and then continues on up to the top and below the diagonal. And what does this say? This says that whereas in this region here of composition of the liquid, the vapor is somewhat more rich in component A than the liquid. When we reach this point here, they're exactly equal. And so this is what we call a constant boiling mixture. Or azeotrope. Constant boiling mixture, meaning that the vapor evolved by boiling is the same as the liquid, so it doesn't change. And typically in a case like that, when you go beyond that, then the component that you've plotted here and called symbolically component A is less volatile than the other component, and so the curves are below the diagonal on the other side of the azeotrope. Now this is typical, or this is illustrated, of course, by ethyl alcohol and water, which you have been given a boiling point composition diagram plotted on a certain basis. Now I thought, before I forget it, I will give you now a table of vapor-liquid equilibria for ethyl alcohol water at 760 millimeters of pressure, in which the data is given in both weight percent and mole fraction in the liquid and the vapor phases, and the temperature is given in both degrees centigrade, degrees Fahrenheit, and this is an example. This ethyl alcohol water system of the one that forms an azeotropic mixture. Now I hand you out another chart which represents the plot of that data, the liquid composition against the vapor composition on a mole basis. So this is the vapor-liquid equilibrium curve. might mention, and this table that I handed out, that there's some other data there that we haven't talked about yet. That part I've written in longhand has to do with relative volatility. And that's a term we haven't used, but we will have occasion to use the word volatility, relative volatility. And it's defined down at the bottom as a ratio of the volatility of component A divided by the volatility of component B. In other words, we use that term volatility sometimes called V as equal to the of a particular component is simply the ratio of the amount in the vapor at equilibrium to the amount in the liquid at equilibrium. And of course, if you divide one by the other, the volatility of component B by its volatility, which is where you get the term we call alpha or relative volatility. And of course, then that simplifies into our the alpha is equal to y sub a x sub b divided by y sub b x sub a. And so those values of mole fractions of x and y can be readily converted onto into the alpha values, which, as I've got here in the column in the middle of the table. The last two columns have to do with something in the future, namely some calculations involved in graphical solution where you need the value of 1 over y minus x. So I'll give it to you now so you'll have it. Well, anyway, we call this represents then an azeotropic mixture, but also one which has which both components are mutually soluble. That is, there's no problem of having but one liquid phase when you put any possible combination of composition together. Now we have a third system, where we have partially miscible liquids represented by such things as isoamyl alcohol and water, or isobutyl alcohol and water, or ethyl acetate and water, where each component is partially soluble in the other, but if you exceed a certain amount, well, then you get two phases present. And the equilibrium curve for for what we call partially miscible or partially soluble system forms what we call a heterogeneous azeotrope, or heterogeneous azeotropic mixture. Now, schematically, if I draw this where x is equal to y, we'll find in the region in which A is still soluble in component B, that the vapor equilibrium curve would look something like this. And then at some value here where the limit of solubility is reached, this line will go straight across until we reach the value which represents the maximum solubility of component B and A, and then the curve will go up something like this to the origin. This is the equilibrium curve. And we call this the heterogeneous azeotrope. And then in a moment I'll draw what would be the comparable composition diagram for these systems. This would be the equilibrium curve for a heterogeneous azeotrope.
What did you say happened at those 2 points where it hits a straight line?
Pardon?
What happened?
This is a region of immiscibility. This is the region of 2 phases. 2 phases. And this is the composition of the azeotrope. Well, let me erase this and yes.
Is that the area of the 2 phases, is that just between those 2 vertical lines?
Yeah.
And then the azeotrope is on either side?
Well, the azeotrope is what this says is that if you take a mixture right here and heat it up to and get the vapor off, you get this composition here. And it also says that if you take a mixture here, you get the same value. So for over a period of quite a range here, as I've illustrated, the vapor given off by boiling a mixture is exactly the same. It'll probably be a little clearer when I draw the boiling point composition diagram in just a moment.
Do you know which one is the maximum concentration of B and A and which is the one with the maximum concentration of A and B again?
Well, think of it this way. This would be 100% A. So as you start to add B, well, you start to move back here. So this point here then would represent the point at which you exceed the solubility of B and A. So over here is this would be the limit of solubility of B in A, considering B the solute and A the solvent, you see. And over here, that would be the limit of solubility of of A, which would be the solute, in B, which is, of course, over here is 100% B. Well, you already have an example, the ethyl alcohol water mixture of the boiling point composition diagram for a homogeneous azeotrope. So I don't know if I need to draw that again as a tip to illustrate the type. But now let me draw the boiling point composition diagram that would be typical of a heterogeneous mixture. I'm not sure it'll be it'll be exactly compatible with that one there, but anyway, it'll be partly so. We would have well, let's say we have, let's see how this is going to be. Have some temperature over here that, let's say this is the temperature of the boiling point of component A in the pure state. And somewhere over here we have the temperature of the component B in the pure state. I failed to mention so far that by convention we usually try to plot the more volatile component of a mixture. for example, here, this represents the fact that between A and B, that in this case, that component A is the more volatile. If we plotted component Y, or B here, why the curve would be beneath the axis, be the reverse. But of course, when you get into azeotrope, why you get a reversal of relative volatility. That term relative volatility, if you calculate it numerically, whenever it comes out to be greater than 1, it means the component that you put first, or on top, is more volatile than the other one on the bottom. But if you just turn it upside down, well, you get a number that's less than 1, naturally. And so then you'd have a volatility that is less than 1, and that, if you're plotting it in a less volatile component, the curve would be below. So, but when it comes to azeotropes, of course, somewhere in the position it reverses, so to a certain extent, the convention is not too important. In the case of ethyl alcohol and water, in the range in which we're interested in, below the azeotrope, ethyl alcohol is more volatile, so we conventionally plot the composition of alcohol rather than the composition of water. But anyway, we'd have, let me draw this, and then I'll explain it. Try to explain it. It'd have about this value here. You'd have all right, now here, these lines here represent the liquid phase, composition of the liquid phase, the one above the vapor phase, the liquid phase, the vapor phase. And this represents the azeotrope, or the constant boiling mixture. And so this says that if we at some temperature down here, which is below the boiling point of either components, if we started, and I'll just draw this line in here or something like that, because that represents really the solubility curves, these little dotted lines here. And this says that if you start at some temperature such as this, below the boiling point of any mixture in the system, and start adding A to the solvent B, that it all goes in solution until you get over to here. Then you have the first appearance of another phase, which really is somewhere over here. This isn't necessarily exactly a straight line, but yes, I guess it is, yeah. And over here, then, this new phase would represent a small amount of component B dissolved in A. So in this region here, we have two liquid phases. Two liquid phases. Over here, we have a single liquid phase. And over here, we have one liquid phase. And so it says that if you have some composition over here where it's still mutually soluble, if you raise the temperature up to the boiling point, that it boils at this temperature. And that the vapor given off from that has this composition. If you condense that, however, you'd have two phases, wouldn't you? That's what you do. So that's what happens. And if you get over to just at this point here, this composition, it boils at this temperature, and the vapor, and the vapor is and composition is this value right here. It says that if you have an overall composition which is represented by some point in here, and you heat it up to the boiling point and have the phases intermix so that they'll have equal opportunity to vaporize, that the same composition of the vapor will be given off. Of course, when it's condensed, it's two phases. It'll be this right here. Same way over here. So the composition of the distillate is not affected by the overall composition within quite a range here, and you do not change it because you do not change the composition of the two phases. You merely have different amounts of them when you're in this region here. Of course, this represents a mixture of liquid vapor phases, and this would be all vapor phase up here, as before. Well, as we'll see later, this is a rather interesting aspect of certain mixtures, in that whenever you have partially miscible or weakly soluble mixtures, in that region in which there is a solubility, you have very enhanced volatility. In other words, the volatility here is very great. In the case of amyl alcohol and isoamyl alcohol and water, the volatility constant is about 35 to 1. Say less than 1/10% of amyl alcohol. So well, I guess our time is up, and so this is the reason why whenever you have a heterogeneous azeotrope, you have a straight line across here as far as the temperature is concerned. And of course, this would be the temperature of this constant boiling heterogeneous azeotrope. And why on the equilibrium curve you also have a straight line across here, because the composition of the vapor does not change within this region here of composition. Well, I guess we better stop at that point, and